All right, derivative of a function, 3.1. Today we're going to do slopes of tangent lines. Lines that are tangent to a curve at a point. And we're also going to finally use the limit definition to find the derivative. We're studying derivatives. This is one of the big topics of calculus. Unfortunately, this is the long way to do the derivative, and I do have to show it to you. So don't be discouraged. Every time we do the derivative, you're not going to have to do all of this work. It is for basically this section, maybe a little bit next section, but then we're going to learn the shortcut. And all of the shortcuts are so much nicer and friendlier than doing it the long way. Okay, to start off, example 1, we're going to start with something we're already familiar with. Find the average rate of change of f of x equals x cubed minus x over the interval from 1 to 3. The average rate of change is basically slope. We're finding the slope of this function between the interval of 1 to 3. This interval represents my x's, my x values. So I'll call this one x1 and I'll call this one x2. To find slope, you always need 2 points. At least that's what you should have learned in algebra. Luckily, they did give me 2 x's. So if I want to find my y values, all I have to do is take my x's and plug them into the equation. So I'm going to plug in 1, and then I'm going to plug in 3. So I get 1 cubed minus 1, and 3 cubed minus 3. So I get 0 and 24. So these values here are my my y1 and my y2. So now I do have 2 points. So I'm going to go ahead and find slope. So slope, if you recall, is y2 minus y1 over x2 minus x1. So I'm going to plug in what I have. y2 is 24, y1 is 0, x2 is 3, and x1 is 1. So 24 minus 0 is 24, 3 minus 1 is 2. So the average rate of change, or the slope, from 1 to 3 is 12. And this is the normal stuff we're used to. This is where this is where slope changes for us in calculus, because finding the slope starts from, okay, you need 2 points, you use those 2 points. But in calculus, you don't have the luxury of 2 points. We're going to be finding slope. It's just that instead of having 2 points, we only have 1. And that's what the derivative is. Finding the slope with only 1 point. Okay, so example 2, find the slope of the parabola y equals x squared at the point P is 2, 4. So here's 2, 4. They gave me 1 point. I have to find the slope at that point, at that very instant. So here when they're saying slope, it's not just the average rate of change anymore. This is just a rate of change. And it's referred to as an instantaneous, I can't spell, instantaneous rate of change. However, the book and most problems usually just say rate of change. They don't actually say instantaneous. So you need to know the difference between average rate of change and rate of change. Average rate of change is the slope the good old-fashioned way, y2 minus y1 over x2 minus x1. Rate of change, or instantaneous rate of change, is finding the slope with derivatives and only using 1 point. All right, so as mentioned before, the problem lies in the fact that I only have 1 point. So to prove my point, we're going to make up another point. In fact, I'm going to call it Q. So we're going to make up another point. And the idea with calculus is that whatever other point you use, you want it to be really, really close to the point that you actually wanted to find the slope of. I wanted to find the slope of 2, 4. So my new point is going to basically be so close to 2, 4 that I can't even notice the difference. You're like, what? Yeah, it makes sense. So I'm going to use 2 because that was my x. But I want my new point to be really close to 2, like 2.01 or 2.0001 or 2.0001. But instead of writing a decimal, some funky decimal, what I'm going to do is I'm going to call it 2 plus delta x. And what that means is 2 plus a little bit. How much or how little doesn't really matter. It's 2 plus something else. It's not just 2. So it's really close to 2. It can be really close to 2. But I'm just going to call it delta x. Now, this is my new x. I need a y. In order to get y, you always take your x and you plug it in. Okay, so I'm going to plug in 2 plus delta x into my function, my equation, over here. So when I plug in 2 plus delta x into my equation, I get 2 plus delta x squared. So here I have my x1 and my y1, and now I have my new x2 and my new y2 that I totally made up, right? Okay, so now we're going to use these 2 points to find slope the good old-fashioned way. So I'm going to go ahead and plug that in. I'm going to write it down. Let's see, x2, or sorry, y2, let's start at the top. It's 2 plus delta x squared minus y1. X2 is 2 plus delta x minus 2. So now I'm going to have to distribute the top. 2 plus delta x, I actually have to expand that. I'm going to pause it, I'm going to do it, and I'm going to write it out. Okay, so I expanded 2 plus delta x squared. I wrote that all in blue. You can see I distributed. And then I ended up with everything under the curly Q here. 4 plus 4 delta x plus delta x squared. The minus 4 at the end is this right here. Okay? Now, you should notice some things on top. For example, this 4 and this 4 cancel each other out. Awesome. Now the bottom. The bottom, if you look at the bottom of the fraction, this 2, well, you know what, let me do that in green. This 2 and this negative 2 cancel each other out, leaving me with just delta x. So this is what I have so far. Okay, I'm going to go ahead and write this on the other line now. Okay, so I just rewrote everything without the stuff that got canceled out on the next line. So now, this is essentially my slope. It looks really funky. I can still clean this up some. The delta x on the bottom, I can get rid of it by canceling out the delta x's on top. Not all of them, but some of them, most of them. So I'm going to factor out a delta x from each one of these terms because they do have them in common. And I'm going to end up with 4 plus delta x divided by delta x. And then that's where they cancel out. So now I have 4 plus delta x. This is my slope. This is actually a general equation that will get me my slope for any single point on this parabola. But I was only really interested in 2, 4, right? But I don't have anywhere to plug in 2. But remember delta x? Delta x is supposed to be like this very minute change in my original x value. Delta x is the change in x. Well, what if, using the power of limits, right? What if I told you delta x was slowly approaching 0? It was getting closer and closer to 0, and so that it would actually end up being the point 2, 4. This original point right here. I mean, the change in my x is going to be so small that it's basically practically zero. So if I do the limit as delta x gets really small, basically non-existent, of this equation 4 plus delta x, well, using limits tells me, oh, okay, so like delta x is 0, or at least you can plug that in, and my answer would be 4. Well, this is what derivatives are, only that after learning the long way, we start doing the short way, the shortcut, which doesn't involve limits as much, but this is the idea of a derivative. I was able to find the slope, which, by the way, if you haven't noticed, the slope of this function is 4. I was able to find the slope, but only using one point. Okay, you're like, but no, you made one up. I mean, did I really? Did I really make one up? I used a bunch of pretty little symbols, but did I really make up the other point? I mean, look back at my cue. If I were to take that and I pretend that delta x is 0, so then here, 2 plus delta x, which is 0, is 2. And then on the right side, 2 plus delta x squared. So if delta x is 0, that's 2 squared, which is 4. Did I really make up a point? No, I really didn't. It looks that way. I tricked you into thinking I did. But my slope is just 4. And you're like, oh, but that's the y value. No, these are different 4s. Yes, it's the same number 4, but it didn't come from the y value. Okay? um, so this is the idea of limit. We're using, or sorry, the idea of derivatives of slope. We're using limits to try to figure out what the slopes are with only one point instead of 2. And then this right here, ladies and gentlemen, is a tangent line. This is not the same tangent as the trigonometry tangent. This is a different tangent. I tried to make that line as best as I could. That line represents a tangent line. Tangent lines go through a certain point on a curve. Sometimes they briefly kiss the curve. Sometimes they go through the curve. It depends. This specific tangent line at the point 2, 4 will have the exact same slope as that point on the curve. If you look at my tangent line and you do the slope the good old-fashioned way, from here to here, so let's see, that's 4 steps up, 1 step to the right. From here to here, that's 4 steps up, 1 step to the right. Okay? This is just the introduction, but please, please don't kill me for all the work. We get to do shortcuts eventually. Okay. Okay, example 3 says write an equation for the tangent to the parabola y equals x squared at the point 2, 4. So that red line from my last slide, we're actually going to write an equation for that line. And if you remember how to write equations, the friendliest version for this class is point slope form. And for point slope form, you need 2 things. You need a point and you need a slope. Let me write that down. Need point and slope. Okay, in the problem, they did give us a point. The point is 2, 4. Have you noticed this is the same information from the last one because I'm gonna make an equation for that line, the red line on my graph. The slope, we just found the slope. The slope is 4. So I have the 2 things I need. So I'm gonna plug them in and I get y minus 4 equals 4 times x minus 2. And then I get y minus 4 equals 4x minus 8. And then I get y equals 4x. I'm going to add 4 to both sides and get negative 4. So this is my equation. that's that. The word tangent. Whenever you hear the word tangent in this class, you should automatically think derivative. Now, I didn't do the derivative in this part. I did the derivative in example 2. That's finding the slope. Derivative is finding slope. I already did the derivative. So tangent's like, okay, I need the derivative to find the slope. We did that already. So in this example, I just had to write the equation. Okay, B, write an equation for the normal to the tangent of y equals x squared at the point P, 2, 4. Okay, normal. Now this is not your normal kind of normal. In math, the word normal actually means perpendicular. So I'm going to fake it. This is the line, the red line from my graph. Sure, just pretend, sorry. The normal would be a line that is perpendicular to that tangent. We have to write the equation of lines that are perpendicular to other lines. And the same rules apply. I need a point and I need a slope. I have a point. And I do have a slope, but the slope only works for the tangent. The slope of a perpendicular line is actually always the opposite reciprocal. So slope is the opposite reciprocal of the slope of the tangent. Of the slope of the tangent. So opposite means positive or negative. If it was positive, then it turns negative, and if it was negative, it turns positive. And reciprocal means that whatever the number is, you're going to flip that baby upside down. So my slope that I'm going to use is going to be, instead of 4, which is positive, it's going to be negative. And instead of 4 over 1, it's going to be 1 over 4. So that's my slope, and that's my point. And that's all the information I need. Once again, I'm going to use the point slope form to write the equation because it is the friendliest version for this class. Oopsie. I didn't mean to put 1 there. And that's it. So, wow, I'm putting numbers where they don't need to be. So y minus y1, which is 4, equals my opposite reciprocal, which is negative 1/4, and then x minus 2. So I get y minus 4 equals negative 1/4 x plus 1/2. Because I distributed, right? So now I'm going to add 4 to both sides, and I'm going to get y equals negative 1/4, and let's see, plus 4.5. You can write, I don't like to do this, you can write plus 4.5, or you could put your big boy or big girl pants on and actually try to figure out what 4 plus 1/2 is in fraction form, because sometimes the problems on the AP exam will be in fraction form. So let's see, this is 8 over 2 plus 1 over 2. So this is 9/2. Okay, I would much rather you do that, but 4.5 is accurate. So who am I to say you must do fraction? Plus 9/2. And that is the equation of the normal. Okay, so jumping back to example, what was it, 2? This right here is the formal definition of derivative. It does use limits. That's why I started talking about limits. And this is the really long way. There is more than one version of this. There's 3. This is the basic, I guess the most basic one. I'm going to show you an alternative one. And the one I did with delta x's, that would be like a third one. That they use, instead of the letter h, they use delta x. So the derivative of the function f with respect to the variable x is the function f prime. You see this what is that called? Apostrophe? It's said prime. You don't say f apostrophe. You say f prime. So the function f prime whose value at x is, and then we have f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So this is basically what I did by hand, just that they're using h instead of delta x, which I guess is friendlier because you don't have to write two things instead of one. All right, now there are several notations for derivatives, and I need you to be able to identify all of these things as being derivatives. So I'm going to write them all down. Okay, so these are all different notations of derivatives. So if you see any of these, that means take the derivative, do the derivative, differentiate. These are all different words that means derive. Take derivative, do derivative. Okay, so the first one in blue, f with the apostrophe x, that's f prime of x. The little words on bottom, that's how you would say it. The next one in red, that's y prime. The one in green, this is dy over dx. This is the derivative of x, and we say it dy dx. That's the best way I could write it out. Just saying the letters dy dx. And then the last two, the purple one, is just, this means you're deriving whatever's in here. Okay, in the brackets that will normally be a function, and the ddx means you're deriving that function. The last one works basically the same way. The last one is the least common. I will never write that. If you see it, you should be able to recognize it as being a derivative. But I can tell you that I will never write that because I'm not used to that at all. I use the other four, and I think it's really like not common. Okay, example 4, find the derivative. So they're flat out telling us find the derivative, which means slope, of f of x equals x cubed plus 2x. I'm going to use the formal definition. So I'm going to pause and I'm going to write some stuff down so you could see. Okay, so I'm going to use the formal definition. Now, I have an f of x. What I need to figure out is what is f of x plus h. So I'm going to go ahead and write that on top so that you could see. Okay, so on top of the green, I wrote out x cubed plus 2x. I left the x on the outside, but you see it's still cubed. And then the 2x, again, the x is on the outside. What I'm supposed to be doing is, I'm supposed to be replacing any x's with x plus h. So it's going to look like this, x plus h squared, or cubed, plus 2 times x plus h. Okay, so that is what I'm going to use in my formal definition of a derivative. So I'm going to go ahead and fill it in. Okay, so I wrote it all out. All the green stuff is supposed to be this part. And then all the blue stuff is supposed to be this part. Okay, now I did write out the green stuff on top. That green stuff, those expressions are going to have to get expanded out. So you're going to have to do x plus h times x plus h times x plus h. And then you're going to have to distribute the two. I'm going to do that off the screen because you should be able to do that. Okay, so I expanded this, if you can see the yellow, x plus h, that quantity cubed, is all of this. And then I distributed the 2 to the x plus h, and that's where the, oh sorry, my bad, where the plus 2x and where the plus 2h come from. And then I distributed the negative to x cubed and 2x, and that's how I get minus x cubed minus 2x. And this is all over h. So this is why I'm like freaking out and saying don't freak out, because I don't want you to be discouraged from all this work. This is not something that's going to happen all year long. I have to teach you this first before I teach you the shortcut. So now I'm going to simplify this best I can. Whatever cancels out, get rid of it. For example, the x cubed here and this x cubed over here, the positive 2x and the negative 2x. And then I'm going to rewrite this on the next line. All right, so this is what's left after the stuff that got canceled. Now if you notice, these terms, there's 1, 2, 3, 4 terms. This one has an h, this one has h squared, so it's 2 of them. This has an h cubed, so there's 3 h's, and this one has 1 h. And then of course this h down here. Guess what? We're going to factor out that at least 1 h from everything on top, and then that h is going to cancel out the h in the bottom, which right now is a problem because eventually I need to plug in h equals 0. So I'm going to go ahead and write that. Okay, so I wrote it out with the h factored out, and of course, like I said, these h's are supposed to cancel each other out. So now I'm left with just 3x squared plus 3x times h plus h squared plus 2. Now this is something that I can plug h equals 0 into. This will go here, it'll go here. So let me go ahead and do that off screen. This is what I end up with. If I simplify it, because I don't really need the zeros, I get 3x squared plus 2. This is a general equation right here of my slope. This will get me my slope for the original equation, which was x cubed plus 2x. This is the derivative. Now the slope part is if I told you at x equals 4. All you had to do is plug it in. Or at x equals negative 2, then you would just plug it in. But this is my derivative. All that work for this itty bitty little thing. Next. Okay, welcome, example 5. I took the liberty of figuring out what f of x plus h would be, and it's 2 over x plus h. Because in this problem, it says find f prime of x for f of x equals 2 over x. So my function is a fraction, no big deal. And I already wrote down the formal definition. So I'm going to go ahead and plug my information in. And what I have is 2 over x plus h, that's the f of x plus h, minus the original, which was 2 over x. And then all of this is above h. Now here I have a problem because I have fractions inside of fractions. And not only do I have fractions inside of a fraction, but the fractions in the numerator don't even have the same denominator. So I'm going to have to find the same denominator for both of them. And I'm going to do that on the next line. I'll write it all out first. Okay, so this is the same thing as what's up there, only I left a little space because I want to show you what I'm going to do. In order to make the numerator, the fractions in the numerator have the same denominator, the easiest way to do this would be to multiply the first term, the one on the left, to multiply that by the denominator of the other. So x over x. And then the second term, I'm going to multiply that by the denominator of the first term. So x plus h over x plus h. This should not be anything new. This should be stuff you already know how to do, right? So this is going to get me the same denominator. So I'm going to go ahead and multiply. Okay, so I multiplied everything out so that they would have the same denominator, and that denominator is x times the quantity x plus h. So I ended up with, on the top, the numerator of the top is 2x minus 2 times the quantity x plus h. Obviously, I can distribute this too, and I'll do that on the next line. But my next problem is I still do have a fraction inside of a fraction. So the best way to get rid of that is the the denominator, which is h. Basically, this is a fraction being divided by another number, and I can call that a fraction too if I put it over 1. And if you remember back in middle school, when you divide fractions, you can actually change it to multiplication as long as the second term gets flipped, or you use its reciprocal. So that's what I'm going to do. I'm going to write it out. Okay, so I have 2x minus 2h, because I distributed the 2, over x times the quantity x plus h. And then I said I had to get rid of that denominator from down there. So I'm going to multiply it by the reciprocal, which is 1 over h. So I'm going to go ahead and simplify because I can see that I have 2x minus 2x. And I'm going to go ahead and rewrite this. Also, I'm going to distribute the x on the bottom. I'm going to distribute this little baby right here. Okay, so now I have negative 2h over h times the x squared plus xh that were technically already there. Now, hopefully you can see that I have an h on the top and an h on the bottom. That will nicely cancel out. So I'm going to cancel those out, and then I'm going to rewrite my problem again. Okay, last but not least, this is an alternative to the formal definition of a derivative using h. Instead of using h, this one uses a, and it looks more like slope. It basically is slope. It's just using a limit. And then I said the third kind was using delta x. Anyway, example 6, differentiate f of x equals x cubed using the alternate definition. So I'm going to write down the definition before I start working. Okay, so you must be thinking, how is this one different? Well, we're using a. So for my f of x, I'm going to use the actual equation, x cubed. For my f of a, what I'm going to do is I'm going to use the equation, just that instead of using x, I'm using the letter a, or the variable a. So I'm going to use a cubed. And then for the bottom, I'm going to use x for x, but then I'm going to use a, obviously, for a. Okay, for any normal derivative or limit, I would be able, or I should check to see, can I plug in a? And if I do, what happens? Well, if I plug in a, and this time the a is going to go wherever the x's are, so I'm plugging in this a where the x's are, the bottom would end up being 0, and we're not allowed to do that. And when that happens, you have your choices. You multiply by the conjugate if it's a rational or a radical. You factor. You can use, what are those called? Tables, stuff like that. You have options. But here, we're going to factor. The top is a difference of cubes. And the difference of cubes, if you remember, I wrote it on the board, and I'll just pause and I'll write down the formula again. We're going to use that to factor the numerator. Okay, as you can see, it's factored out, and because I factored it out, these cancel out, which is a good thing because I can't have a fraction if I can't plug in my a. So now I'm left with x squared plus x times a plus a squared. And technically, now I can go ahead and plug in my x equals a wherever there's an x. So I'm going to end up with a squared plus a times a plus a squared. So let's see, what do I actually have here? I have a squared plus a squared plus a squared, which, if I know how to count, is 1, 2, 3, 3a squared. This is my derivative. Now, if I told you, okay, find the derivative, but when x equals 5 or x equals 2, then what you would do is you would plug in the 2. So let's say I wanted the derivative at 2. So you would do 3 times 2 squared. So that's 3 times 4, which is 12. And that would be the slope at that point, which is x equals 2. But right now we were just finding derivatives. Next class we'll be finding derivatives, but not this really long way. Please do your homework. Have a good weekend.